So this assumes there's no loss. So here let's see how the loss. So sender sensor package 0 is acknowledged. Now when it sends package 1, it's lost. Then there's a timeout. After this timeout is depleted, then the sender will resend that package 1. Then hopefully that will be received by the receiver. The receiver can acknowledge package 1. Then you can continue. Okay, so in here, we actually don't have a sequence number. They just alternate between 0 and 1. But that's actually a very good question. So if you don't have this packet number, then how does the receiver know, are you sending this package over and over again, or this is a repeat of the previous package? And this is an animation about what happens if there's acknowledgement loss. Let's say the packet 1 is delivered, and this acknowledgement is lost. So the receiver will wait, then send the packet 1 again. So now receiver will detect a duplication. It will send an acknowledgement again. So that's why you need a package sequence number so that it knows it's not a duplication. So finally, what if there's a premature timeout? So here, the receiver received the packet 1 correctly, and it sends an acknowledgement. But this acknowledgement got delayed during the transmission. So the sender would not know if that transmission is en route. It will basically send this packet again. The receiver will receive a duplicate packet 1. It will just send this acknowledgement for packet 1 again. At the same time, the first packet may receive here. But in either way, the receiver can ignore the second acknowledgement. It just knows if it sees received one positive acknowledgement, it knows that this packet 1 is delivered. So once it receives the acknowledgement for this packet 1, it can send the next message. So here we can see we actually didn't use a package number. We just alternate between 0 and 1. So in this case, we actually can deliver a reliable data transfer that can handle errors in the data loss. Then how about performance? Uses the channel in a very inefficient way. So we can calculate that. So let's say you have a 1 gigabyte link. There's only 15-second propagation delay. And then you got a 8,000-bit packet to send. So if you remember from the first chapter, we can calculate the transmission delay here. Just take the size of the packet divided by the bandwidth. It takes only 8 microseconds to send that packet from the sender to the receiver. But how long to actually use the entire channel? So remember, it takes 15 seconds to propagate the packet from the sender to receiver, and then while waiting for that acknowledgement back. That means you have to use the one entire round trip time to deliver that one package. So if this round trip time is 30 microseconds, that's twice of this 15 seconds. Then that means you can only send 1 kilobyte package for every 30 microsecond. Another way to think about this is this is a T0. It takes L divided by R time to push those bits into this transmission channel. And this is the trapsoid we really shows the time we actually use the channel to transmit data. So now it's delivered. Then we have to wait for the receiver to deliver the acknowledgement. Then when the sender receives the acknowledgement, it can send the next package, right? So the utilization rate is calculated by basically this blue trapsoid divided by the total trapsoid that's used in here. So L minus divided by R, that's the blue trapsoid, the width of here. Then the total trapsoid area is basically proportional to this width times the round trip time. So that's a very, very small use of the bandwidth of this channel. So how do we get around this problem? Yes, that's right. That's pipeline inference. So basically, you can send one packet, then after another packet, send another packet. Then in this case, the sender can keep sending a whole sequence of packets, but then it just waits for the acknowledgement to come back. Then when it receives the acknowledgement to a certain packet, it knows that packet is delivered. But of course, if something is missing or something is corrupted, it can always resend some other, those particular packages. And this is called pipelining. Yes?
So earlier we were using just 0 and 1 and alternating between them. Does that not cause a problem now? Because you could have two different ACK zeros.
Yeah, that's Atkins' question. Yes, then you need to use a sequence number.
Okay, nice.
So we can calculate how does the pipelining improves our utilization rate of the communication channel. So here is the time you use to send the first packet, and this is the time you send the second packet. This is the time you send the third packet. And then for the first packet, when it's delivered, the first acknowledgement will come back in here. That means in this time, during this time, you can use all this time to transmit data. And that essentially you tripled your transmission, your utilization rate. And this is the time you're sending out 3 times more sizes of packet over the same bandwidth. But here you are just still waiting for 1 round trip time. So of course, if everything works, you can fill up the entire channel and just wait for the acknowledgement to come back. So we got a good question. How about if we just use 1 and 0, then of course we don't know which one is missing, which one is corrupted. So we need a sequence number in the packet header. And then somehow we have to keep track of which one is corrupted by looking at the acknowledgement, or which one is missing by looking at the lack of acknowledgement. And to do that, there's 2 schemes that you can design. You can do that. One is called a go back N, or GBN. What it does is to maintain this sliding window here. So these vertical boxes means the packets that need to be delivered. And then in here, the send base means all this packet on the right side is a packet that has been delivered and received a positive acknowledgement. That means they safely delivered to the receiver. But now in this yellow boxes here means they have been sent, but the sender hasn't received the acknowledgement back. That means they have to be prepared. Some of them may get lost, so they are still in the window. And then these blue boxes means they are in the sender's buffer. They are ready to be sent, but they hasn't been sent yet. So we have to keep track of these 2 indexes. Send base, that means who is the oldest send package, but they haven't been acknowledged, and who is to be delivered next. And then usually the sender will maintain a fixed window size of n in its buffer. So as you can imagine, as the acknowledgement comes back, this window will basically slide into this direction, right? Basically, this is also called a sliding window pipeline. So one advantage of doing this way is you can actually use something called a cumulative acknowledgement. So imagine that if you have to send a million package and the receiver has to send a million acknowledgement back, that's a lot of return traffic. So what you can do is, since you know this package is delivered in sequence, then you can actually just send one packet for the previous n consecutive received packages. That's called a cumulative acknowledgement. Another way to think about it is I receive the first package, a second one, the third one, I acknowledge the third one. When the sender receives the acknowledgement for the third one, it automatically considers that all the previous packet has been delivered without any error. So that means from the sender side, once it receives the acknowledgement on this blue box, for example, it will just consider all the other blue box has to be delivered. It will move the slide window toward this side. Yes?
So say we get an acknowledgement for the first 2 yellow bars,
right.
Then we don't get an acknowledgement for the third, but we get acknowledgements for the fourth. Does the window only move up 2?
No, it moved to the fourth. Basically, it receives all the acknowledgement. It considers, let's say you receive the fourth one, right? Then you consider all the previous one has already been received.
Well, but if we don't receive the acknowledgement for the third one?
Yes, that's okay. It's called a cumulative acknowledgement. That means if I receive the fourth acknowledgement, that means all the previous one has been acknowledged. So basically, this is just a way for a receiver doesn't need to send all the packet acknowledgements. I can skip a few.
So if you didn't have the cumulative, would you only move up to however many you had seen?
Right. That's how you can do it here.
Okay.
So basically, it remembers which one has been acknowledged, which one hasn't. So the advantage of this is you can reduce the acknowledgement traffic. Yes.
If you acknowledge a packet that is at spot 10 or
Yes.
something, it assumes that all previous packets will be received.
Yes. So now the other problem is what if let's say you receive the packet number 10 or the number 9 has been lost, right? Then what does it do? So actually in that case, the receiver will actually discard the received packet number 10. Basically, it's waiting for the sender to do a timeout on the packet number 9, then it will deliver number 9 and deliver number 10. So of course you can think of this as a wasted transmission, right? The number 10 has been delivered, but all you do is actually just deliver number 9. So that's actually this kind of design. You acknowledge every single packet, and the receiver, the sender will keep track of which one has been acknowledged, which one hasn't. It only resend those packets that hasn't been acknowledged. So the advantage is you can do a gap filling here, but the disadvantage is the receiver has to send a packet acknowledgement for every single packet. Right, that's the pros and cons of these two designs. In practice, TCP uses a combination of these two designs to do the pipelining. So let's go into the actual how it's implemented. So this is a few things we talk about is built upon pipeline segments, accumulate acknowledgement, then a single retransmission timer. So for simplicity, let's first don't worry about the duplicate acknowledgement or flow control and the congestion control. For the sender side, we have a few events here. One is if we the sender received a data from the application, that means upper layer, we got some data that we need to send. First, it creates a segment with a sequence number. The sequence number actually is not the number of packets, it's actually the bytes. So for example, right now, let's say we are in the byte 10. We received something we deliver a packet that has 10 bytes. It will just increment that byte to 20. So this sequence number counts number of bytes. And if you don't have the timer running, so the sender will start a timer. It basically counts down from the oldest unacknowledged segment. When the timeout is triggered, they will resend the packet that has the constant timeout. That's the oldest unacknowledged packet. Or you can also receive an acknowledgement. That means you can mark which one has been acknowledged and then move your window forward. And this is another to visualize this process to find a state machine. So first, the sender waits for the event, receive data from the application from above, create the segments, then set a sequence number, that's the next sequence number, then pass the segment to the IP. So that's the underlying unreliable data sending channel. Then it increments what's the next packet that's going to be delivered, that's the next sequence number. If the timer hasn't been started, start a timer. So just to remind you, we are basically in here. So I have my send base here. So once I send, I can keep track of this is my next send number. That's the two numbers we are going to be keep track of here. So next sequence number. And of course, we haven't changed the send base yet. That will be updated when we receive a package. So when we receive a package, if this acknowledgement of the acknowledgement field is 1 is more than our base, then we update this base to 1. And then if there's no other unacknowledged segment, then we can start the timer again. So basically, we can start from the timeout anew. Right? Finally, if there's a timeout, then you can just retransmit the segment with a smaller sequence number.
So we only have one timer. We don't have one timer for each packet?
No.
So then if you send 10 packets all at once and you have a timer on the first one, right? And say that one doesn't get out for a while, how would you know later on if you need to change the timer to the new oldest unactivated? How would you know when it's time?
Right, so here you have to start timer again. So when you receive acknowledgement, so for example, the oldest one is the package number 10, then I have a timer on this. So now I receive acknowledgement, so I can basically reset my timer, right? So basically I move to my oldest acknowledgement to number 11.
So you just restart, okay.
So it's always to restart timer when you receive the acknowledgement. So we can run through a few scenarios here. So here we'll actually use a more realistic sequence number that counts bytes. So first we have a sender that hosts A here, and then right now it sits at a sequence number 92. So it sends 8 bytes of data. And then remember the acknowledgement we acknowledge is the next expected byte. So it basically asks this number, say, then source B will want to acknowledge I have received this packet, and my acknowledgement number is 100, and then this is lost. Then the sender will wait for a timeout here. Then we resend the package again, then in here. So next, let's say we have a premature timeout. Then this sender will send this two packages back to back here, 2 packets. So sequence number is 92, 8 bytes of data. So remember we're counting bytes, right? So the next packet will start from sequence 100. Then it has 20 bytes of data. Then when the receiver receiving it, they can acknowledge 100. That's acknowledging this packet, 192 plus 8, 100. Then you also receive the second package. It actually acknowledges 120. That's 100 plus 8, 20 bytes. That's actually this. When it receives all this, it will actually update the send base. So before it's 92. Since it receives acknowledgement for 100, it updates the send base to 100. Receives another acknowledgement, then updates the send base again to 120. So in this case, we also are simulating a timeout event. In here, since the acknowledgement is not received in time, you send this again. But in this case, you are seeing something interesting. It actually acknowledged 120, even though this is sending the data is only 100. It's because we are doing the cumulative acknowledgement, right? The acknowledge is the latest one that received. So just acknowledge the most recent received packet. Okay. Yes.
Will host 8 know to keep going if it receives the ACK 120 at the end?
Yes. So basically, this is going back to design. It will keep a window size n. So this is usually max. Basically, it's depending on the buffer size of the sender. It will keep sliding this forward whenever some acknowledgement received. And this is another example of a cumulative acknowledgement. So we have this package sent from here, and then this package is lost. Then in the next package actually delivered, so the acknowledgement number will be this sequence number time plus is 20, then acknowledge 120. So when the host A received this, even though it didn't receive this acknowledgement, it still knows that all the previous package has been acknowledged. Then it will go ahead and deliver the next package. Then let's say this the sequence number will be 120, then 15 bytes of data. So on the receiver side, there's yes.
So if we run the TCP Python scripts that you gave us and we send like a gigabyte file over it, will it automatically chunk it up and do this?
Yes.
Okay.
Yes. So you are working at the application layer. So that's all this data will bind to. The TCP layer will chop it up for you.
So in this scenario, when we don't get the acknowledgement for 100, does the timer reset for the 100 packet or the 120 packet?
So you set timer here, right? When you see this timer here, the timer will be reset for this 120.
Okay, so we just ignore that we didn't get the 100.
Right, right. So this is benefit of cumulative acknowledgement. Yes.
If the first packet sequence that you do was lost,
Right.
but the second was still received,
Right.
what would host B respond with?
So first, it would not respond to this, it will not acknowledge the second packet, right? Because if it acknowledges, that means it received the first one. So usually there are two options. If there's no fast retransmission, you just wait. Basically wait until this host A to deliver again. So now on the receiver side, you have two options. You can keep this the second packet in the buffer and wait for the next one to fill that gap. Or you can just drop that one, and assuming the sender will send it again. So this is assuming there's no fast retransmission. There's a one way you can do a fast retransmission by doing this duplicate acknowledgement. Okay, let's stay with this more simplified scenario. On this receiver side, there are a few things you can. There are a few scenarios you are going to be in. So first, you receive the in-order segment with expected sequence number, and then this is all up to the expected sequence number is acknowledged. Then you can see it actually delays the acknowledgement. So for example, I got a number, the packet number 10, 11, 12. I don't just send it right away. I wait for 500 milliseconds. So in case the next one comes in, I don't need to keep resending this acknowledgement, right? So this is how we can save some bandwidth by doing the other way around. But if you receive the in-order segment, there are other pending segment waiting acknowledgement. They right away send some acknowledgement to acknowledge all the previous packets that has been received. Now this is an out of order segment, higher than expected number. That means you are expecting the packet number 10, or you receive it packet number 11, now have a gap. So there's a way for the received tail sender, I'm missing one packet in the middle. That's by sending a duplicate acknowledgement. So what this means is if I'm expecting packet number 10, and I will receive the packet number 9, right? I'm actually number 9 over and over again. And of course, after you acknowledge this missing packet, you can also get that segment right away. So when you receive something that fills gap, you immediately send this acknowledgement. Well, so this is about this fast retransmission. That means the sender will receive, if the sender receives 3 acknowledgements for the same packet data, they know there's a gap here. And this is an example. Host A sends a host B a packet. And this first packet, one packet that's start from 92 with 8 bytes of data. The next packet will start from 100 with 20 bytes of data, and that's lost. But the third package is delivered. All right, but then this one is also delivered. This one is also delivered. So now you can see the response. This one has delivered without any error, acknowledged 100. So this is lost. So now the receiver receives something that's out of order. It knows it's missing something. It keeps acknowledging the first one that has been received previously. So notice that it didn't actually receive acknowledging this package delivered out of order. Basically, it keeps acknowledging the previous one. So when the sender receives the 3 triplicate acknowledgement, it knows that it's missing the receiver has a gap here. It receives a sequence number 100 with 20 bytes of data. And notice that the sender the timer hasn't run out for the timeout yet. Yes?
So there's 4 acknowledgements. So the first one is the original, the second one is the first duplicate, and then it's first duplicate, second duplicate, third duplicate.
No, this shows 5 different packets.
Right, we know the acknowledgements. So there's 4 acknowledgements.
Oh,
there.
yes.
So it's original, first duplicate, second duplicate, third duplicate.
Yes.
Okay.
Yeah, so that's why it's called a triplicate duplicate.
Duplicate. Okay. Got it.
Any other question here? So this is why, go ahead.
Why does it need 3 duplicates?
Right, you could do it with 2. Somehow the designer decided they need 3 to do this fast retransmission. And going back to this go back and the selected, they kind of combine the advantage of both. So first you use accumulate acknowledgement. Basically, when you acknowledge something, that means all the previous acknowledgement I acknowledge the second has been received. So it reduces the number of acknowledgement packets. It also allows you to selectively repeat. That means you acknowledge something 3 times in duplicate. That means you have to give me that to fill my gap. So let me ask you a question. Let's say this is in this kind of case, the sender receives something here. Then what's the acknowledgement?
Whatever the last number is of the one.
Right,
received.
right, that's right. So basically, you accumulate acknowledge all these things you have received so far. Like it fills all the gap. Yes.
So, if the receiver sends an acknowledgement for something that wasn't where you started, so say for example, receiver sends back acknowledgement 95. You never started a transmission at 95, you only started at 92 and 100. Shouldn't you know immediately, oh, it didn't send back the stream?
So first you cannot, so in this case you cannot have the 95 here, basically. So you know, the sender knows it sends, the sequence start with 92, it sends 8 bytes there, expecting something that's the number 100. If you receive something acknowledged like 95, that's,
Well, so if the receiver only gets the first 3,
oh, I see. Then the entire package is lost. So basically, it's either the entire package is delivered or it's nothing is delivered.
Oh, so these are bytes, not packets. I thought we were sending good packets. Okay. I understand.
Right, right. So TCP is a byte stream, it counts bytes. And then we will just skip this code. So here is in this finite state machine, we have another counter here to count how many duplicate packages that we receive here. Okay. So since we are running out of time, so let's just skip this in-class exercise. Let's continue on the lecture. If you have more time towards the end, we can work on this exercise. Otherwise, I just leave that as a homework with the solution provided. Okay, so in TCP, we have covered a few features. So this is a summary. So firstly, it provides a point-to-point communication. That means one sender, one receiver. And it guarantees you reliable in-order byte stream. That means all this packet lost or corrupted packet is handled for you underneath the in the TCP layer. It's pipeline. But this is also managed with a consideration for congestion and flow control. So we won't be able to cover these two parts. It's a fully duplex data, so that means the sender receiver can send the package back and forth. The channel goes both directions. And usually you can set this maximum segment size. So I think there's a question about that. So if you send dump a 1 gigabyte of file, then TCP will chop it up to this size of packet. Usually it's about 600 bytes. And it's connection oriented. That means before you can send data, you have to do a handshake. And also there's flow control. This is how a TCP segment look like. So the overall structure is very similar to the UDP. You have the data here, and you have a header here. Then first you start with the 2-port number, a source port number, and destination port number. And this is the sequence number, and this is the acknowledgement number. So remember, when we are talking about here, acknowledgement number and the sequence number here, they go to these two fields here. And then there are some flag here you can set, and also there's this checksum here. In the acknowledgement, in this base sequence number, you have byte stream. So I think I want to say this again. So remember, it's counting bytes. The reason I'm stressing this over again is you have a homework on this. So remember, you are counting bytes in the sequence number. And the acknowledgement is actually an acknowledged sequence of next byte expected from this other side. And you are doing that cumulative acknowledgement. So if you look at on this side, basically you are sending you have to think about this. Each box here actually stands for a byte. A packet may cover multiple bytes. So how does the receiver handle out of order segments? You can either buffer it, wait for the next segment to fill the gap, or you can just drop it and hope the sender will resend it again. And this is where you keep track of the second number. So this is and this is the acknowledgement number. That means this is acknowledged so far. Okay, so let's count the bytes again using the one example with the telnet. So telnet is very similar to SSH. You log onto a machine, you press a keystroke. That means you will send a packet to the server. Server will send you a packet back to display a character on your screen. So in this case, the user needs to send a packet C, that means one character. Then the sequence number is 42, acknowledgement is 79. So this is initialized to some random value at the beginning of the connection. Then at the same time, it has a data in the payload as a C here. When the host receives the C here, it needs to echo back a C, right? So when it sends a packet back, so this is the sequence 92. It also acknowledges the 9043. So you can see that we actually don't have a dedicated acknowledgement packet. It just acknowledges in the reply. This is 92 because previous sequence is 40. This is 43 because the previous one is 42. It receives 1 byte, then increments this acknowledgement to 43. So now the host, that's your laptop, receives that. It wants to echo something back. Then in the next payload, you increment this, you use the acknowledgement as the sequence number, then acknowledge what you received as the character C. So 1 byte plus is 79, then that's equal to 80.
So do each host and receiver, do they have to have like a different thread for sending and receiving, because you can't be both trying to send and waiting for a response at the same time?
In the actual implementation, it's probably multi-threaded. But you can conceptually you can think of it as blocking. So basically, you can wait for the receive,
Okay.
then you don't do anything. Then when you see something, acknowledgement. So one thing I want to emphasize is if you look at all this traffic back and forth. So here, even though we said it's acknowledgement back, this is actually not just an acknowledgement packet. You actually can send this useful data inside the payload of the acknowledgement packet. Connection management is about how do you build a connection between a sender and receiver. First, they have to agree on to receive effective connection, and also they need to agree upon this connection parameter. So this gives you a list of parameters. So first, they have to agree on what's the sequence number. So remember, they don't actually start from 0. Actually, they will pick a random number. So you need 2 sequence number. One is client to server. The other one is server to client. In a 3-way handshake, something that you hear a lot about. This TCP. So what's a three-way handshake? So before the two process can exchange data, TCP actually needs them to acknowledge 2 things. One is the client needs to know the server is ready to receive and send. And the server also needs to know that the client is ready to receive and send. So it's only with these 2 pieces of information they will start to exchange data. Then why does this require a 3 handshake? So this is the first handshake. So first, let's say client sends a packet in this client state, the client doesn't know if the server is ready to receive or send. It just sends a packet to the server. So now the server receives something from the client. So now server knows you got a client that's ready to send since you received something from the client. But server doesn't know if the client is ready to receive or not. Right? It just receives something from the client. Now this is the first handshake. And then to do in the second handshake, the server sends a packet back. So this doesn't change the server state, but the client knows something new. Since the client receives something from the server, it actually needs two information. One is the server can receive data, because otherwise it will not send this second handshake back, right? So it must have received my first packet to the server. Second, it also knows the server can send the data to this client. So this is the second handshake. And then this is the third handshake. The client needs to send a third packet back to the server. So why is this needed? Because in the second handshake, the server still doesn't know if the client is ready to receive. It just knows that the server can send some package here to the server. But it doesn't know if it will actually respond to this acknowledgement. So this is the third handshake here. And in the third handshake, there's something special here, because the client, when you finish the second handshake, it already knows the server is ready to receive and is ready to send. It actually can send the data in the payload of the third handshake. So actually, you just waste time of two round trip time with these two, the first handshake, second handshake. And this is the status of the two sides. First, the client start with the listening mode. Then it sends a package. Then it switches to the sync send state. And this also carries the sequence number. The client tells the server that this is the sequence I'm expecting. So now servers start with listening mode. Once you receive something, it goes to the sync received mode. Then it will actually send an acknowledgement back called a sync acknowledge. Then it will acknowledge two things. One is this is my sequence number, that's Y here. And also I acknowledge the previous packet you sent to me, so that's X plus 1. So the X here, X plus 1. Then this is, after the second handshake, the client will consider the connection to be established. So now it actually can send payload in this data back to the client, to the server. Once the server receives, then this connection is established. So in this process, when we are doing the three-way handshake, this is accomplished by this welcome socket. And after this welcome socket establishes the connection, it passes all this parameter to the connection socket. Then the transmission actually can start. After you finish the transmission, then we have to close the connection. So that's pretty straightforward. You call that close command, then this is a special flag you have to set the finish bit. Then also the server acknowledges that closing connection command. Then it itself also closes that connection. Okay. So I think we have a bit of time to do this exercise, so we can work on this. So maybe 5 minutes. The first question is, if a client needs to send some data to a server as quick as possible, how much delay does this three-way handshake create? The second question is, what advantage does UDP has over TCP? And what are the advantages of TCP over UDP? So I put this figure here to help you with the first question. Okay, so let's work on these two questions together. So let's say the client needs to send some data to the server. So with UDP, you just send it right away. There's no delay. With TCP, you need to go through this three-way handshake. But of course, this is the tricky part is this doesn't actually count because the client can sense data on the third handshake right away. So basically, the delay is this one round trip time. Then the transmission starts here. Question? Okay. So of course, this is something you always need to consider. We covered this from the beginning. We have two options from the Internet Protocol stack, UDP versus the TCP. So UDP, one advantage is that it can have one quick initialization of the data transfer. Specifically, that's one RTT quicker than the TCP time. The second one is it has less overhead. So UDP, the packet header is only 8 bytes, but TCP has more than 20 bytes of header. So this is the overhead for the transmission. And UDP doesn't have a congestion control. That means it just can send out the data over the network without considering the congestion. For the TCP, the main advantage is it provides a reliable data transfer. It guarantees you that all segments will be delivered without loss, in order, and without error. It also provides the congestion control. That means the whole network will become smooth, running more smooth if everyone is using this congestion control. And because they have different features that are being used for different applications. So for UDP, the main application is the domain name service, DNS service, and also real-time video, audio streaming. So you can see that both of them require a very quick initialization, and also they don't want to have a lot of overhead. But they don't require reliable data transfer because missing 1 byte doesn't create too much problem in real-time streaming service. TCP is mainly used by HTTP, email, FTP. So this all requires reliable data transfer. Okay. So let's a quick summary, this is what we covered so far. So we talked about the principle behind the transport layer and also the comparison between these two protocols. Okay, so this concludes our segment on network programming. So we only have time to talk about the application layer and transport layer. So, but I think this should give you a very good starting point for you to practice socket programming.
So for next class, the quiz 131 and 132 are homework.
So I will upload a solution. Just work on the quiz by yourself and then submit something.
Still groups or not?
I will try to do that.